John, can you unmute? John, unmute. Yes, John, good afternoon.
Good afternoon, sir.
How are you today?
I'm fine, sir.
Good. John, can you open this session with a prayer?
Okay, sir.
Can you pray for us?
Humble
Okay,
soul,
please.
sword of prayer. Dear Lord in heaven, thank you for the gift of life. Thank you for the breath of life that you give unto us. Dear Lord, as we come unto thy throne of mercy this afternoon, we are requesting for your wisdom, knowledge, and understanding so that we may get whatever that she is going to teach. Come and be with us. Let your Holy Spirit come and tabernacle with us. In thy name I have prayed. Amen.
Amen. Thank you so much, John, for such a wonderful prayer. Really, I'm blessed with the prayer. I would also task you again, Joan. Are you hearing me?
Yes, sir.
To remind us briefly what we studied in the last lesson, please.
So in the last lesson, we studied about thermocouple.
Thermocouple.
Its advantages, how it works, and its operations. Maybe
briefly you can tell us the advantages of a thermocouple over other thermometers. Hello, Joan.
Yes, sir.
Can you tell us the advantages?
So it can measure temperature.
Very good.
Yes, sir.
It can measure temperature at a point, right?
It measures temperature. Yes.
Oh, great. Can you add for us the second one?
Changing temperature. It is used to measure rapidly changing temperatures.
Very good, very good, very good, very good, very good, very good. Let me ask Stephen. Stephen, can you unmute? Okay, George, can you unmute? Stephen, can you hear me? Stephen? Okay, let me pick. Yes, Stephen. Stephen, you can unmute. Stephen? Oh, sorry. Let me hear from Frank. Frank, can you unmute? Frank? Okay. Let me hear from Justin. Justin, can you unmute? Oh, these people are not unmuting. So what we're going to do, I wanted you to remind us what we studied in the last lesson. Justin says I was absent. It's okay. Fine. Let me hear from those who are present. Can you raise up your hand, those who are present? Can you raise up your hand? Those who are present, can you raise up your hand and then you remind us about our lesson? Okema Alfred, I remember you were present. Okema Alfred?
Yes, sir.
You were present, right?
No.
Oh, you were not present?
I have just joined today.
Oh, you have just joined today. Sorry, it's okay.
Okay, yeah.
Who was present? Raise up the hand, please. John says you also studied about constant volume gas thermometer. Actually, let me give the chance to John to tell us everything. John, can you unmute?
Yes, sir.
Okay, please go on and tell us everything we studied. Constant volume gas thermometer. What did we say it is and what are the advantages? What other benefits do we have? What are the disadvantages? What are the sources of errors in constant volume gas thermometer? Thank you so much. Please go on.
I will start with the preparation. Okay, how we use it to calibrate temperature at a given point.
Yes.
So the gas bulb is inserted. The gas bulb is put first in the at the steam point, and the temp and the pressure is also recorded and measured.
Yes.
After that, it is also inserted in a temperature at ice point. Also, the temperature recorded. After that, it is also put in the substance at which its temperature is supposed to be taken, and also the pressure recorded. Then from theta is equal to p theta minus pressure at steam point minus pressure at ice point times 100 degrees Celsius. Then the temperature can be obtained.
Saturated. Okay.
Then the advantage.
Yes.
The advantages include it is very sensitive.
Very
That's
sensitive.
the first one. Yes.
Then two.
It has a wide range of temperature from
Can have a wider range of temperature.
1,500 shares.
Okay, good.
Then it is accurate since pressure at a fixed mass of gas is at constant volume varies linearly with temperature. Very,
very good. Very, very good.
Then the fourth one.
Yes.
It is used to calibrate other thermometers.
Very good. It is used to calibrate other thermometers. Good. John, what are some of the, let's say, disadvantages?
It is bulky.
Bulky, very good.
Then it has no direct readings.
It does not give the direct reading. Very good. Then what are some of the sources of errors?
It cannot measure rapidly changing temperature. The temperature of the gas in a dead state.
Very good. There is
thermal expansion of the bubble.
Oh, great. Oh, those are the ones which you studied in the last lesson. Today, we are going to see something else. Please, the notes for last lesson is already in Google Classroom. I posted long ago, that very day. And this one will be there right after here. So today, we are going to see what we're calling to be pyrometers, and we shall enter into calorimeter. Pyrometers, then after pyrometers, we shall enter into calorimeter. I welcome each and everybody for being here. Joy Lovins, you're most welcome, Joy Lovins. You can say hi to us, Joy Lovins.
Thank you, sir.
Okay, please. Fine. You see, Joy Lovins had never missed my lesson, any of my lessons. She's ever there in the lesson. So today we are going to see pyrometers and calorimeter. And for those who have just joined today, my name is Teacher Daniel Alira. I teach physics and mathematics, and I like physics most. Why? When I'm talking physics, I feel like I'm eating some nice porridge. Very sweet as eating porridge with sugar. We are glad we are being sponsored by CSO, Edify Uganda, under an umbrella of Christian School Owners Association with sharp brains from Itao, Uganda. They have given us this opportunity to study online, even for free. We thank God for them. We pray that God continue to bless them, to always bless the pocket where they are getting all this money from to sponsor this great program. I challenge you to take this program very serious and make sure you benefit a lot from it, especially for those ones who have just joined today. Today, we are going to see pyrometers and calorimeter. Pyrometers and calorimeter. Good. Who can tell us briefly what you know about pyrometer? If you know anything about pyrometer, you can raise up your hand. Say, teacher, I know something about pyrometer. How does it look like? What does it do? How does it do it? And what are the advantages? What are the disadvantages? How is it different from other thermometers? Something of that type. Can somebody tell us briefly what he or she knows about pyrometer? Wesongoma. Wesonga. Yes, Wesonga. Your name is complicated, my brother. But let me hope you are not always disturbed when I call you a wrong name. Yes?
Any risks?
Good afternoon.
Good afternoon. How are you?
I'm fine, thank you.
Good.
About pyrometers, I know there are two types of pyrometers.
Very good.
There is the total radiation pyrometer and is it optical pyrometer?
Very good. There are two types of pyrometers, total radiation pyrometers and optical pyrometers. Do you know how to differentiate between the two, Wesongoma?
It's Wesonga.
Hey, Wesonga, for sure, yeah. Sister, I'm very sorry for that, okay?
It's okay, teacher.
Wesonga. Do you know how to distinguish between those two types of pyrometers?
Not really. Okay, all I know is that for the optical pyrometer, it uses radiations from a hot body. But then for the total radiation pyrometer, all I know is that there is something to do with reflection of the light rays. I'm not sure.
Okay, I see you have the idea. Good. So I think from here you will get to know very well, okay? Let me first pick somebody to give us the definition, the difference. It's used to measure very high temperatures, i.e. temperature of the furnace. That one is from John. John is trying to tell us about pyrometers. Good. Joy Lovins, your answer is up. Joy Lovins. Thank you so much. Wesonga, okay? Let me hope I pronounce very well now. Joy Lovins.
Yes, I'm like I want to try.
Please go on.
As in, it is a device used to measure high temperatures of radiations.
A device which is used to measure high temperatures of radiations. Very good. It's a device which is used. What we need to know about it is that it measures very high temperature. Now, to answer the other question, which was not answered by our sister, Wesonga, is the types of pyrometers. We have basically two types of pyrometers. We have total radiation pyrometer, and we have what we call to be optical pyrometers. Our sister Joan is saying total radiation pyrometer responds to total radiation. Okay, good. Now, let's differentiate between the two. We have total radiation pyrometer. Total radiation pyrometer responds to both heat and light. Let me come again. Total radiation pyrometer is sensitive. It responds to, it detects both light and heat from the body. Then when we talk about optical pyrometers, and optical pyrometer, optical, optical, when we talk of optical, it's just light. That is optic, light only. So optical pyrometer responds to only light. Remember, total optical pyrometer responds to both, total radiation pyrometer responds to both light and heat. But optical pyrometer responds to only light. Wesonga, have you gotten the difference between the two now? Hello, Wesonga?
Yes, teacher, I'm okay now.
Okay, please. So those are the differences. The main difference between the two, Alfred Okema says, he's also very okay with it. Well, that's great, Alfred Okema. To today we are going to see them, the two. You're saying, just like how somebody has put it across, there are two types. Before you look at the two types, they are used. What we talk about optical parameters, parameters, they are used to measure very high temperatures, like temperature of the furnace, temperature of fire, temperature of the sun. Which are the temperature? I've given temperature of the sun, temperature of fire, temperature of the furnace. Who can give me another temperature? Temperature of what? You can even type in the chat. Justin, temperature of what?
Magma.
Temperature of magma. I like that. Temperature of magma. Magma is very hot, hotter than any other thing. I don't know. Frank. Frank, temperature of what? Frank. Temperature of what? Oh, Frank has kept quiet. The sun. Wesonga says the sun. I've already talked about the sun. You are repeating it, and I wanted you to repeat. It's okay. So we are saying pyrometers are used to measure very high temperatures, like temperature of the furnace, temperature of the sun, temperature of magma, as somebody has said. Okema said temperature of tungsten filament. Very good. And we use also to measure the temperature of tungsten filament. They are subdivided into two. What are called to be pyrometers are subdivided into two, which I've already given you. We have total radiation pyrometer, which responds to what? The response to total radiations, i.e., heat and light. Please, we have total radiation pyrometers, which responds to heat and light. Then we have another one, which is called optical pyrometer. Optical pyrometer responds to only light. So for it does not respond to heat. So it responds to what? It responds to only light. Those are the main types of pyrometers, optical pyrometers, and then total radiation pyrometer. So if I ask you to distinguish between the two, then it becomes very simple for you. You say optical pyrometer responds to only light. Total radiation pyrometer responds to only, both heat and light. Let's talk about optical pyrometers. When you see optical pyrometer, it looks to be very nice. I like optical instruments because the way they are designed, they look to be very nice. You can see that optical instrument. It is optical pyrometers. Optical pyrometers. Now, if I asked you, can you describe briefly the structure of optical pyrometer? Briefly, the structure of optical pyrometer. What would you say? Who can tell us briefly the structure of optical pyrometer as you see from here? Raise up the hand. Optical pyrometer. Hello? 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 Optical pyrometer. I see people are still thinking about the answer. Just raise up your hand and you speak. But there are some people who have never talked in my class. For sure, if you have never talked in my class, I don't know whether you can ever talk in anybody's class, because at least I give John Ellipse. John Ellipse. John Ellipse. Unmute. Okay. John Ellipse has kept quiet. We are seeing the diagram here. How can we describe the structure just? What are the components of optical pyrometer? That's what we mean by possibly the structure. Yes, John.
So the filament.
Yes.
Okay, when you're describing, I think we're going to talk about how, okay, that what is used to make up the whole thing work, so?
Yes.
So the filament is focused by the eyepiece, and the hot body is
Yes.
focused by the objective lens, so that the image of the object lies in the same plane as the filament.
Oh my God, good. Oh, when is your birthday? When your birthday comes on the day we have a lesson for physics, we shall sing for you birthday song. Have you heard?
It's already passed.
It has already passed. Sorry, Bambi. Maybe we shall sing for the younger sister.
Has also already passed.
Oh my God. Now what do we do for you? For sure, you have made the lesson very interesting. So, thank you so much. If your birthday was coming ahead, we would sing for you happy birthday. The whole physics class. Good. So we're saying that if you looked at this diagram, you can really realize that it is made up of two lenses. There's a tube. There's this tube. We can call it to be a cylindrical tube. So this cylindrical tube contains this lens. This lens is called optical lens, but we give it a special name, and that special name is objective lens. Then there is also this lens at this end, which is called to be optical lens, which is called to be eyepiece what? Eyepiece lens. This is eyepiece, and this is what? This is an objective lens. So the objective lens, the work of the objective lens is to focus. I'm going to describe everything from here. The work of the objective lens is to focus the hot body onto the filament. It focuses the hot body onto the filament. Then the work of the eyepiece is to pick light from the filament and takes it to the eye. You can see this eye. So the filament is attached to the circuit in the lower part here. Physics tells us that when current flows through a conductor, that conductor heats up. A filament is unable to produce light unless current passes through it. And what does current do? The current does something just very little. It just heats up the filament. When it heats up the filament will become red hot. Remember, the temperature of this body is very high. That's why I've even used the red object. Now, there are two hot bodies here. I connect the circuit. When I connect the circuit, current will flow through the filament. When current flows through the filament will also be hot. So its color will automatically change. It will be red hot. So in this case, we have two hot bodies. We have the filament and we have the hot body. So the light from this object is focused onto the filament. Now, when light from this filament, from this object is focused onto the filament, the combination is then focused onto the eye by the eyepiece. Now, two things will happen. Not will, but may happen. One, if the temperature of this object is greater than the temperature of the filament. Remember, the filament is hot. So that means it has its own temperature. And the object is also hot. But there are two things which may happen here. One, when the temperature of this object is higher than or greater than the temperature of the filament, then what you see here, using your eyes, you will see a dark filament in a bright background. Let me come again. When the temperature of this object is higher than the temperature of the filament, what this person will see, he will see a dark filament in a bright background. Then two, if the temperature of the filament is greater than the temperature of the body, then you will see a bright filament in a darker background. Now, whatever the case may be, a moment you see that there is a dark background with a bright filament. That one should tell you that the temperature of the filament is greater than the temperature of the body. A moment you see that there is a dark filament in a bright background, that should tell you that the temperature of the hot body is greater than the temperature of the filament. Now, when you realize that, what do? You either increase the current through the filament using this rheostat. This is a rheostat. You increase or reduce depending on what you found out. You reduce the current through the filament or increase the current through the filament. So we use a general term. We say you adjust the rheostat. You adjust the rheostat such that the filament in its background is indistinguishable. I mean, you cannot tell that this is the filament and this is the background. When the filament disappears in the background, when the filament vanishes in the background, when the color of the filament is the same as the color of the background. In other words, until when the background and the filament are indistinguishable. Now, at that point, you make a conclusion that the temperature of the object is the same as the temperature of the filament, and the temperature of the filament is read direct. There's a milliammeter here. Is read direct from the milliammeter, of which that becomes the temperature of the filament, which also becomes the temperature of the object. Is that clear, members? Please let me know. Oh, Okema says clear. Is that clear, members? Please let me know. I want to know. If it's not clear, I'm free to repeat. I can repeat my explanation. I'm here for you. Is that clear? You can use the chat, you can use the signal, whatever the case may be. Is that clear? Hey, Salua says, very clear. It's clear, sir. Justin says it's clear. Oh, good. Oh, good. It's clear. Justin says it's clear. Nabudu says it's very clear. So that's briefly, thank you. That's briefly how it works. You focus, you first pass the current through the filament will be red hot. Then you focus, using the objective lens, you focus the hot object onto the filament. Now, two things may occur. When the temperature of the hot body is greater than the temperature of the filament, then the filament will be dark in a bright background. When the temperature of the hot body is less than the temperature of the filament, then the filament will be bright in a dark background. Using the rheostat, you adjust the current flowing through the filament until the filament and the background are indistinguishable. At that point, it means that the temperature of the filament is the same as the temperature of the object. So you read directly the temperature of the filament from the milliammeter, which gives you the temperature of the object. Okay, good. Marilyn says, clear. It is very clear, sir, but a clarification. What's the golden circular object after the filament? Okay. This golden circular object here is trying to show us how the filament and the background should look like. It should be indistinguishable. So it should be like this. You can't see the filament and you can't see the what? The background. Everything is background. So it's like there's no filament. Then somebody is asking, where is the filter placed? Filter can be placed, I mean, you can place on both sides. You can place filter here and here. We place it here to remove the stray what? Stray light. One direct light onto the what? Onto the filament. So that is that when it comes to that. Good. Let's see. Marilyn has a hand up. I don't know. Let me pick Marilyn. Yes, Marilyn.
Thank you, sir.
Yes, please.
I'm still clarifying about that object that I asked about. Is it more like some kind of translucent object?
The circular one? Is this the circular thing here?
Yes.
Yeah, this one is like, okay, it cannot be a transparent one. You know, there are two mixtures. We have the color of the what? Color of the filament and the color of the object. The two will meet. When they meet, as long as you're not seeing the filament, okay? Because you want the filament to disappear in the what? In the background, okay? So the color, I've just chosen a translucent one here so that you don't see the what? We don't see the filament to illustrate that. Is that okay?
Yes, it is.
Okay, please. Good, good, good. So that is briefly the optical pyrometers. Let's go to how it works. Mode of operation. I'm going to be, I've already explained this. We're saying that a hot body whose temperature is required or whose temperature to be measured is focused by the objective lens. So when you focus by objective lens, you focus it onto the filament. That's why you're saying that it's focused so that each image lies in the plane of F. F is not focal length, but the filament. After that, the light rays from both the filament and the body pass through the what? The red filter. I told you the filter can be, you can put the filter beginning and at the end on both sides just to remove the stray light. So the light rays from both the filament and the body pass through the red filter to the eye. Then the image of the hot body is brighter than the filament. If the image of the hot body is brighter than the filament, this one I've already told you, when the object, which is the body, is hotter than the filament, then the filament becomes black, or I mean dark, but the background will be what? Bright. And if the filament is hotter than the body or the object, then the filament will be bright in a darker background. So when you notice any of the two, you make sure you adjust the current through the filament so as to increase or reduce the current flowing in order to reduce or increase the temperature respectively. so that at least at last, the two cannot be distinguished. That's why we're saying that using the rheostat arrow, you have the current through the filament is adjusted until the filament cannot be distinguished in the background. Oh my God. Until the filament cannot be distinguished in the background. Then from there, at this point, the temperature of the filament of the hot body is then equal to that of the filament. And you read the temperature direct from the milliammeter, which is calibrated to read the temperature. Good, 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 good. Any question? A question is allowed. Joy Lovey says, is it on or in the darker background? In the darker background, is it on or in a dark background? The most important thing is that the filament should appear in a dark background or on a dark background. Oh, you can use on. Yes. Is there any question you can raise up? If you have also submission, please, you can also submit. I like senior 5, 6. When you're dealing with senior 5, 6, you're dealing with matured people. And so their submissions also matter a lot. Is there anybody who would wish to submit, who wishes to say something? Please. Or I go ahead with other things. Okay, great. Let's move on. The next thing is the advantages and the disadvantages of this. Justin says, let's proceed. From what you have seen with optical pyrometers, we have already discussed the structure, how it's made, how it works. What do you think are the advantages of optical pyrometers? Please, Joy Lovins.
Start trial.
Please go on.
It is used to measure temperature of moving objects.
Used to measure the temperature of moving. I encourage you to always add there, moving and distant objects. Is that okay, Joy Lovins?
Okay.
Oh, thank you so much. It can measure the temperature of moving and distant objects. Very good. I see another hand, there's no hand. Can I see another hand? Please, please, please. Joy Lovins again. Please, 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 wait, Joy Lovins. Okay, let me see Wesonga. This name is punishing me seriously.
Hey, teacher. Anyway, it gives direct readings.
It gives the direct reading as you read from the milliammeter directly. Good. Webale munonga, wesonga. Okay, Joy Lovins.
So I think it is also very accurate.
Very accurate. The accuracy is there. The accuracy is there. John, I want you to speak that answer. Let me pick you. Okay. John, can you talk? John?
Yes, yes.
Can you talk?
Yes,
speak
sir.
your answer. I saw it, but you speak it out.
It measures temperature over a wide range.
It measures wide range of temperature. Good. There is one which people don't want to tell me. Me, I'm waiting for it. Actually, there are two. Joel, are you sure you're going to tell me the answer? What I want to hear?
Just trying.
Okay, please try it out.
Okay, measures temperature of object without being in contact.
Very good. You go to campus. Joel is tomorrow, pack your things and go to campus. Yes. That was too good. It measures temperature without being in contact, with the body. We've been discussing other thermometers. You have to bring the body, bring the thermometer, put at ice point, put at steam point, put in the body whose temperature is required. But here, we don't need to bring the body in contact with that, okay? Then the last one which I want to hear, please, the last one which I want to hear, Frank says it is portable, okay? Joy Lavis wants to complete my very good today for sure. What will I tell people tomorrow? Okay, Joy Lavis.
So what about measuring temperature quickly?
Quickly, okay. Oh, but the one I wanted was it measures very high temperature. Actually, this is the thermometer which measures the highest what? Temperature. Do you know measuring the temperature of the sun? Do you know the temperature of the sun? Too high. And this thermometer is able to measure it. Let us discuss the disadvantages. What do you think are the disadvantages? But for sure, there are some people who are not talking. Fortunate. For sure, if I call you and you keep quiet. Shana Ashom. Shana.
That was me. Yes.
Yes, Fortunate. Bisingura.
Yes, sir.
Please, can you give us the disadvantages of optical pyrometers?
Of optical parameters.
Yes.
I can talk of inaccuracy.
Inaccuracy? I think you can even tell us about the cause of inaccuracy.
The what?
What brings about the inaccuracy? What are the sources of inaccuracy?
I think because of the environmental changes.
Oh my God. Thank you so much, Fortunate, for such a wonderful submission. It is because, remember, like if you are to measure the temperature of the sun, we have air molecules. Sun is very far from us, but the optical parameter has to be on Earth. And so we have dust in space. We have even natural occurring radiations are there due to radioactive substances. We have smoke particles in space. So all this can easily affect the accuracy of optical pyrometer. Thank you so much, Fortunate, okay?
You're welcome.
Good. Frank says it may easily damage eyes due to high temperatures. We get light, we don't get the what? We don't get the heat. When it comes to optical pyrometers, we pick light from the sun, not heat from the sun. Good. Okay, let me. Wesonga says, what of the air layers from the earth? Yeah, those are the sources of errors. Joy Lovins having the hands up. Joy Lovins, today you have taken it all.
I think it measures the temperature based on light intensity.
It measures temperature based on light intensity. That is true. Yeah, because it uses light. The temperature based on light intensity. But how is that disadvantageous? How is it disadvantageous? Justin, I want your answer to be spoken. Can you speak your answer? Justin, where are you? Justin, can you raise up your hand? I've seen you. Can you unmute?
Okay.
Speak your answer.
Okay, thank you, sir.
Yes.
I think it is expensive.
Very expensive, very expensive. Have you ever seen optical pyrometer anyway?
No.
I know. You have never seen it, and yet you know other thermometers, but you have never seen the other one. So it's very expensive, very expensive. Good. So those are the advantages and disadvantages. Then maybe, or to add on, optical pyrometer cannot measure very low temperature. In other words, it cannot measure what? Low temperature. Is that okay? It can't measure low temperature simply because of one thing. Let me explain this. It cannot measure low temperature simply because it detects radiation. Okay? So for a radiation to be produced, the body must be hot. There's no cold body that can produce what? Radiation, unless maybe if it's a radioactive substance. If it's a radioactive substance, it can produce those radiations, alpha particle, beta, and gamma rays. But these other normal bodies, for them to produce radiation, then the temperature must be very high. So cold bodies do not produce radiations, and so its temperature cannot be measured using optical pyrometers. Good. I see Melanie with hands raised up. Yes, Melanie.
Oh, thank you, sir. I'm sorry to take you back.
It's okay.
About the structure of this pyrometer, the optical pyrometer.
Yes.
Is it the only structure? Is it the only structure of an optical pyrometer? Because there's one I saw where we have the objective lens, then the filament is right after the objective lens, then the red filter, and then the eyepiece.
Then there's a red filter and then the eye filter.
Eyepiece.
I told you, as I said, you said the filters can be put on both sides, okay? The filters can be put on both sides. We have the filter on the side of the objective lens, okay? Then the light from the filament onto the what? The light from the filament, before it reaches the eyepiece, it also passes through the what? Through the filter. Do you get me?
Yes.
Yeah. So there can be a filter on the side of the objective lens and right after the filament. Is that okay?
Okay.
Yeah. And the use of the filament, the filter, I've already told you to remove the stray what? The stray lights, okay? To absorb the stray light, okay?
All right. Okay.
Good. So the diagram has no problem. Is that okay?
It's okay, sir.
Good. Thank you. Thank you. Thank you. Let's see disadvantages and advantages of this gentleman. One, it is used to measure very high temperature. Optical pyrometer is useful for high temperatures. Then two, it can be used to measure the temperature of the moving object. Somebody had already told us, temperature of the moving object, and not only moving object, but also distant object. Then I like this. Its accuracy, and lastly, no need for contact. So whether the hot body is in heaven or on earth or underwater, as long as you can focus that body onto the filament, full stop. It's like a telescope. The telescope, you don't need to be where the body is. You just need to focus it. As long as it is in a place where you can focus, you can measure its temperature. That's why you're saying we can measure the temperature of the sun. Who has ever reached the sun? Is it possible to even be closer to the sun? Nedda. You can never reach the sun unless when you want to dry like a like a dry tree. Okay, so no need for the contact. And I like this optical instrument, I mean the optical pyrometer, because of that fourth advantage. Now assume that you are going to use constant volume gas thermometer to measure the temperature of fire. I don't know what can happen. Or you're going to use thermocouple to measure the temperature of fire. Or you're going to use what? Or you're going to use the liquid in a gas thermometer to measure the temperature of fire. You put it in fire. I don't know what can happen. Sometimes I thank the physicists because they did a lot. There are very many alternatives. For any problem, you find there are very many alternatives, and the best ones, of course. So for you to measure fire, the temperature of fire, you don't need to go to where the fire is. No. Get your optical pyrometer. Use the objective lens. Focus the objective lens onto the fire. Put the filament there. Put the light on. Then focus it. Is the filament dark in a bright dark background? If the filament is dark in a bright background, that means the temperature of fire is more than that of the filament. If the filament is bright in a dark background, that means the filament is hotter than the fire. Adjust the current flowing through the filament until when the filament and the background are indistinguishable, read directly from their milliammeter. You get there. Good. Then disadvantage, of course, much as it has advantages, that one cannot stop it from having disadvantages. You've already given me some of the disadvantages. The accuracy is affected by dust, smoke, and thermal background radiations. I gave you an example. When we are talking about sun, measuring the temperature of the sun, there are very many distractions that can disturb sunlight before it reaches the earth. One of which is the dust. Secondly, smoke particles which are there. We have very many particles, even air molecules themselves, they are problems. So those ones can affect the accuracy of the optical pyrometer. Then the second one is that for it cannot for sure measure any temperature which is very low. That is true. I've already given you the reason that low bodies with low temperature do not emit or do not radiate radiations. Do not emit radiations. Optical parameters are able to measure only the temperature of those bodies which emit radiations. And so if the body is cold, it is unable to emit it. Then next is the reason why it's not readily available, and that is because it is expensive. Very, very expensive. Buying it, I don't know how much. I don't know how much it costs, but it's very expensive. You can even Google it, or you go and check on Jumia whether it's there. So those are the advantages and disadvantages of optical pyrometers. I think at this point, we have seen that optical pyrometer is actually different from other thermometers. Is that true? I think we have already seen that optical pyrometer is now different from other thermometers. Who can give me how is optical pyrometer different from other thermometers we have been discussing? West Songa, you said it's correct. Joy Lavins, you said it's okay. Can you give me how is this optical instrument, optical pyrometer, different now from other thermometers? You can raise up your hand. Yes, Joy Lovins.
I think
Yes.
for it to measure temperature of bodies that without being in contact, but other
Very good.
temperature.
It
Okay.
can measure the temperature of the body for sure. Joy Lovins, today,
Yes.
I don't know. Today you're speaking only, I don't know. I'm very happy for you. Yes, Justin. Justin, unmute.
Yes.
Yes, go on and tell us the difference. Yes, Justin. Okay, let me hear from Wesong.
It doesn't use calculations to get the temperature. The temperature
Doesn't
is
use?
directly read. Calculations to get the temperature.
Oh, it gives
directly
direct
read.
reading. Okay, good. Thank you so much for the submission. But the thing is, these other thermometers you have been seeing, you have to bring, just like how Joel Lovins has brought it to us, you have to bring the thermometer in contact with the body whose temperature is required. I see Ashom Shana says, optical parameters function with the current, while others do not. Yeah, that's also okay. But the main difference is here. With other thermometers, you need to bring the thermometer in contact with the what? In contact with the body. What about optical parameter? You don't need it. For parameters, you don't need. Actually, we give them a name. We say they are remote sensing what? Sensing thermometer and non-contact measuring device. Justin says there's no need for fixed points. You don't need a fixed point for what? You don't need the fixed point. The other one, you have to get the lower fixed point, put it in the steam, get in the upper fixed point, put in the body, do this, then calculate from theta equals to p theta minus p naught over p and This one, they are very hectic. This one, just adjust after read directly. We don't need a fixed point, that this is the upper fixed point, the lower fixed point. Thank you so much, Justin, for that. So we're saying the main difference is here. A thermometer needs contact, while pyrometer is a remote sensing thermometer, a non-contact measuring device for high temperatures. So I want us to mark that well. Good, good, good. So those are the differences between thermometer and pyrometers. Oh God, I'm going to send some work on Google Classroom. That work includes all the questions they have ever asked in UNEB about thermometry. Do you hear me? I'm going to send the work on Google Classroom, which includes all the questions they have ever asked about UNEB on thermometry. So that you will be using for revision to revise on what we have just covered and we have just completed. Please try as much as possible to revise. So that is that when it comes to that. So we have calorimeter to start. Now, we have very few minutes. Remember, we started our lesson a little bit late. So we are stopping at net 20. It's approaching time for lunch. Actually, it's already time for lunch. We are stopping at 1:20. Good. Now, calorimetry. Calorimetry. Before I talk about it, we know our stomach. I normally use our stomach if I'm to explain very well what I want to bring out. The stomach contains the liver, the heart, the intestines, the what, the pancreas. I'm not a biologist. I'm not a doctor. I'm a teacher, you people. But the liver, I mean, the stomach contains those things. Now, in these things, when you open the stomach, don't open, but when you open it, you'll find these things are not settled at all. You find the stomach, I mean, the liver is moving here and there. The heart is also pumping. The what is also doing this. The intestine, they're also doing this. So when you're seeing from outside, you see as if the stomach is just stationary. No, it is not stationary. You see from outside that is stationary, but it's not stationary. There are movements taking place. So we say the stomach do have their own energy. It has its own energy. And the energy of the stomach is what is going to be the internal energy. When you see yourself seated, or you see a chair or a table being placed there, you may think that the table is not moving. The table is moving. The atoms of the table are vibrating. Though for solid it is minimal. But when it comes to liquid, liquids do vibrate. Even without disturbing them, they are vibrating. Because matter tells us that matter is made up of a Brown's motion. It says that matter is made up of smallest particle or smallest molecules, which these smallest molecules are in their random haphazard state of uniform motion, even when you have done nothing to them. So the energy of those molecules, they are what we call to be internal energy. Now, internal energy is the energy of the molecules, the energy of the system. Internal energy is classified into two. Internal energy may either be latent heat or specific heat. Let me come again. It may either be latent heat or specific heat. So in this calorimeter, we are going to be studying about specific heat and latent heat, of which the two gives us what we're calling to be, give us what we're calling to be internal energy. So in our introduction, we're going to talk about that. We say the heat energy of the system is internal energy, and it can be either heat capacity or latent heat. To start with is heat capacity. Heat capacity in physics, we denote it with a capital C. When you see a capital C along the way here, please just know we are talking about heat capacity. Who can define for us heat capacity? Please, let's do it very fast. Heat capacity, we have 4 minutes. Yes, Shalom. Nabudu, you tell me the second name for sure, Nabudu.
It's Nabudo Shalua.
Salwa. Oh, yes, sister, can you tell us heat capacity?
Heat capacity is the amount of heat required to raise the temperature of any given mass of a substance by 1 Kelvin.
Very good, very good. Any given mass of a substance by 1 Kelvin. That is great. So we're saying heat capacity is the quantity of heat which is required to raise the temperature of any given mass of a substance by 1 Kelvin. Heat capacity, capital C, is given by Q, which is the heat, divided by change in temperature. So when I use this expression, that means that heat alone, I think heat alone, which is Q, is the same as heat capacity times change in temperature, delta theta. So heat capacity is measured in joules per Kelvin. That is its SI unit. It is in joules per Kelvin as the SI unit. As we wind up, let's see specific heat capacity. Who can define for us specific heat capacity? Specific heat capacity. Oh, specific heat capacity. Yes, Henry. You don't have audio. Henry, yes. Andre? Okay. Salowa?
Yes, teacher.
Can you define for us heat capacity?
Specific heat capacity.
Yes, specific heat capacity.
Specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram mass of a
Very,
substance.
very,
by 1
very good. Amount of heat which is required to raise the temperature of 1 kilogram mass of a substance. The other one was required to raise the temperature of any given mass. So specific heat capacity is denoted by small c, and you're saying that it's a quantity of heat which is required to raise the temperature of 1 kilogram mass of a substance by 1 Kelvin is given by C equals to Q over M delta theta, where M is the mass. Then from there, we can get that. The SI unit is joules per kilogram per Kelvin. So from there, you realize that there's a relationship between heat capacity and specific heat capacity, which you are going to see in this. Then we end up the lesson. So when you remember equation number one was like this. Q equals to C delta theta. Equation number 2 also, Q equals to MC delta theta. So this is 2, this is 2. So we can equate this to that. When we equate, we shall have C delta theta equals to MC delta theta. Delta theta will go. You remain with C equals to MC. So heat capacity is the same as mass times specific heat capacity. Is that clear, members? Okay, good. So that brings us to the end of our lesson. I will send the notes on our Google Classroom, but don't forget, I've told you that I'm going to send also the work for thermometry, all those which have been asked in UNEB on our Google Classroom. I will send them there. So you get there and then you do them. Otherwise, thank you so much for being part of this. Please, I beg that you make the best use of the materials you are getting during this time. I believe they will help you a lot. Thank you. Have a nice lunch.
Have a nice lunch too.
Thank you. Goodbye for now.